Okay, so on the last video, we were talking about graphing rational functions, and part of the process, and most students would agree the trickiest part is finding the horizontal asymptotes of a rational function. On the previous video, I discussed the idea of using limits to find the horizontal asymptote, because what you're always trying to do if you're looking for a horizontal asymptote, I'm just going to draw like a random graph. The only reason to put a dashed line, meaning a horizontal asymptote, is because you want to show that your function starts to approach that number as x goes to infinity, or as you've seen in many cases, it also approaches that number as x goes to negative infinity, right? So even if you don't use limits in whatever pre-calc class you're in, you're essentially talking about the idea that if x approached infinity as a limit, what would your y value approach? So let's just look at this random one. We're not going to graph this. We're just going to focus on horizontal asymptotes and discuss a shortcut that often gets taught in pre-calculus because they don't really want to talk about limits yet until you get to calculus. So if we were looking at this limit, trying to find the horizontal asymptote, imagine let's just start with positive infinity. If we were to plug in infinity, square it, multiply it by 6, that's infinity, add 5 times infinity, which is infinity. Oh yeah, and then add 4 to that. Kind of jokingly, right? Because if you add 4 to all these big, huge numbers, it's not going to matter much. But the point is, when you plug in infinity, you get infinity on the top. And if you plug in infinity, you're going to get infinity on the bottom as well. And one of the points I made on the previous video is that when you see a limit that represents infinity over infinity, it's not settled. We don't know what that's going to be until we do a little more investigation on this, right? There's different sizes of infinity. That's not necessarily going to be one. Also on the previous video, I talked about how you can sort this out by dividing each term in your fraction by the biggest power of x in the denominator. I'll rewrite that again. So that's divide by biggest power in, that's an IN, in the denominator. This is how most likely how you'll do it in calculus. There are slightly different versions of doing the same thing, but so we're going to divide everybody here by x squared. That's your biggest power of x in the denominator. And if we simplify this, 6x squared over x squared is just 6. This term just becomes 5 over x, 4 over x squared, 2 plus 3 over x plus 1 over x squared. It's a lot easier to see as x goes to, now we can bring in negative infinity, whether it goes to plus or minus infinity. 5 over a really big positive or negative number is going to get really small. That's going to go to 0. Same thing here. Any number over plus or minus infinity is going to get infinitely small, leaving me with the answer 6 over 2, which is 3. So in this case, my horizontal asymptote would be y equals 3 if I was graphing this. Let's talk about the shortcut now. And perhaps you've noticed this in just the few examples we've done. The final answer, what did it come from? That 3 came from 6 over 2. And if we trace it back to the beginning problem, what's special about 6 over 2? Those two numbers are sitting right here. Notice that those are the coefficients of the highest power of x in the top and the bottom. And what we also saw was all of these remaining terms essentially just disappeared. They were insignificant. They got infinitely small when we imagined x going to infinity. Now, let's talk a little more about that. Obviously, if you plug in infinity here, 5 times infinity is infinitely big. 4 compared to infinity is insignificant. So to me, it's not too super surprising why the 4 and the 1 didn't matter, right, in the world of infinities. But it might come as a little bit of a surprise that the 5, I mean, we plugged in infinity, 5 times infinity is infinity. Same thing here, but those two terms ended up not really mattering in terms of what the limit is. It was these two. So why is that? Well, in the world of infinities, think about this. If you take infinity and square it, how does that compare to just regular old infinity? Think about this. If you take infinity and square it, that's infinity times infinity, right? Which means it's, if you have regular old infinity and you multiply it by another infinity, you get infinity squared. So infinity squared is infinitely bigger than just infinity, which is why these terms didn't really matter. They didn't contribute to the limit. So this brings up the idea of a shortcut. If you're looking at a limit as x goes to infinity, one way to say it is the limit is controlled by the highest degree terms in the numerator and the denominator. Okay, and then we kind of address why does this make sense, right? We're talking about the biggest power of infinity. So we could just focus on, so let's, like if we were to look at this limit again, and this is, if you're in my class and you are going to be taking calculus, you might want to still do it this way because you're going to do it that way in calculus, that your professors will want you to do it that way. But so it's a good idea for practice, but to shorten up the process for now, and probably a lot of pre-calculus classes, they're not using limits to do these, but it can be shortened up though. If I was doing this limit again, I now would know that if I focus on the highest degree term on the top and the bottom and ignore everybody else, so in other words, I'm just going to say that that's going to be approximately just the limit as x goes to infinity of 6x squared over 2x squared, and I can see those cancel out, and I can just say my limit's going to be 3. In fact, now you could probably just look at it now, right? If you just looked at those two terms and realized 6 over 2 is just going to be equal to 3. Okay, so that's makes this process a little bit shorter. Let's see some more examples here. So if I was trying to find the horizontal asymptote of this function, I'm thinking about the limit as x goes to plus or minus infinity. Okay. We can now just focus on the largest term in the top and the largest term in the bottom. So I'm going to say this is going to be approximately equal to the limit as x goes to plus or minus infinity. Notice my biggest term here is negative 8x cubed. My biggest term on the bottom is 2x cubed. And x cubes will cancel out, and I get an answer. Negative 8 over 2 gives me positive 4 would be my limit. It can be that easy. The largest power of x in the top and the bottom controls the limit. If you go back, if you look at this example and the one before, you'll notice that the powers in the top and the bottom were the same, and it just became the ratio of those two coefficients. What happens if I have a function where the powers are not the same? Here my degree is only 1 on the top, and on the bottom it's 2. So if I was looking at this limit, I still focus on the biggest term on the top and the biggest term on the bottom. So that would be the equivalent to saying, what's the limit as x goes to plus or minus infinity? My biggest term on the top is just 3x. On the bottom, it's x squared. But what does this equal if I reduce that? 3x over x squared is the same as 3 over x. And if x went to infinity or negative infinity, this is just going to go to 0. So my horizontal asymptote would be y equals 0. And you may have picked up on this before. Do you see that's always going to happen? If your biggest power of x is in the denominator, just think of it in the world of infinities. That means you have a really big, this infinity you're getting in the denominator is infinitely bigger than this one. And what happens to fractions when denominators are big? They get small. So if the degree of the bottom is greater than the top, the horizontal asymptote will always be y equals 0, as we saw here. That's a 0. Well, what's the other possibility? What if my biggest power of x is in the numerator? This one's probably the most complicated of the three. Now, again, we're just doing horizontal asymptote for right now, although we might end up graphing this function. But so if I was looking at the limit as x goes to, let's start with positive infinity. And I focus on the biggest term in the top and the bottom. The biggest term on the top is x squared. The biggest term on the bottom is just x. And that's really just x. Well, if x went to positive infinity and I plug that into what's left over, I am going to get positive infinity, aren't I? What would happen if, so let's do this underneath here. What if I had x going to negative infinity? Well, the function that I'm left with is just x. If you plug in negative infinity, you're going to get negative infinity for that limit. So the only way you'd get a horizontal asymptote is if your limit was equal to a number. That would say your y values are starting to level out at some number. If you get infinity, either one of these, that's basically telling us there is no horizontal asymptote for this function. So we could generalize here, if the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote, and your limit, let me add on to that, your limit will be equal to either positive infinity or negative infinity, right? It kind of depends on where x is approaching. However, in the world of graphing rational functions here, we could still get not a horizontal asymptote, but what we call an oblique, also called a slant or a tilted asymptote. That would be an asymptote that's not vertical or not horizontal, but something at an angle. Okay, so we might as well talk about this. So to find it, and that was the case here. Well, hang on. Let me rewrite my function. The way it works is if the degree of the top is greater than the bottom by 1, I'm going to add to this. If the degree of the top is greater than the bottom by 1 power, which is the case here, then you will get an oblique or a slant or a tilted asymptote. Now, how you find it is we're going to rewrite this fraction by using long division. That's something we were talking about earlier. Rewrite using long division. You actually could do synthetic division if you want to. It's a binomial there. I'll go ahead and do the long division. I've done that in a little while. So if I put an x there, that's going to generate an x squared, which is good. I want to subtract that out, minus x. Those cancel. 2x minus negative x gives me 3x. Bring down the minus 5. Now I'd want to put a plus 3 there. That gives me 3x minus 3. Subtract those. 3x cancels. Negative 5 minus negative 3 is just negative 2. And remember how we write that. That's our remainder. So we could say this is equal to x plus 3 plus negative 2 over x minus 1. And so that's the same thing as our function. And so to find that oblique asymptote, the idea is we're going to take the limit again as x goes to, let's just stick with infinity, of this, because it's my function, just written in a different way. What happens if x goes to infinity? 2 over infinity minus 1, that is going to get really, really small. So that's going to approach 0. And if x goes to positive infinity, Infinity plus 3 gives me infinity. Not surprisingly, because that's the limit we got when we did the limit with the original function, so it shouldn't be anything different. But what this tells us is our graph approaches infinity along this line. Graph approaches infinity along the line y equals x plus 3. That's our slant or oblique or tilted asymptote. So let me show you, I think to see the picture of the graph, it'll really help see what's happening here. So rewrite my function again. Okay, we've learned some skills about graphing here. So we know, in addition to this, we know there's a vertical asymptote. Remember, we know how to find vertical asymptotes. There's going to be one at x equals 1. This is our slant asymptote, y equals x plus 3. So that's a line with a y-intercept of 3. Let's call that 3, not necessarily to scale. And a slope of 1, so up 1 over 1. That's going to look like this. Here's our tilted asymptote. We do have a y-intercept that's pretty easy to find. If you plug in 0, you're going to get a y-intercept of -5. And if you try to find your x-intercepts, you're going to see that there isn't any in the numerator. That doesn't factor into something nice. And if you try to use the quadratic formula, it won't give you any real numbers. So what happens with the graph? I'll just cut to the chase here. It's going to approach. Oh, remember the idea of a vertical asymptote being classified as opposite? On this side, the graph goes down. And what happens is it bends around. It doesn't have any x-intercepts. And then it starts to approach this tilted asymptote. Since it's an opposite vertical asymptote, that means on the left side it went down, on the right side it's going up, and it bends around and it starts to approach this tilted asymptote in that direction. Notice these limits are still true, right? As x goes to infinity, it does go to infinity, right? The function does head up towards infinity, and in the opposite direction it goes down to negative infinity. But it would approach that tilted asymptote. Okay, more videos to follow with more examples of graphing rational functions. And from now on, we'll go ahead and use our shortcut for doing the limits by just focusing on the highest power of x in the top and the bottom.